we have a guest speaker coming in. He's Sam, and I'm gonna find him in here real quick because there's so many people in here. Oh, there he is. There's Sam. And so Sam was a student. What was this? A year, 2 years ago, something. 2 years ago. Gosh, that already. COVID makes it seem like eternity, I guess. But Sam had me for 110, and then 161 and 163, I think, back in the day. And also Sam worked with me doing some controls work. He wrote up a GUI for me on I think that was a Raspberry Pi with the tablet, right? And he did all this awesome work, and then I handed it off to some folks up at Cal Poly that were supposed to use his work, and lo and behold, their senior project, they spent much more time writing than doing. So I guess it's learned by writing up there. I hope people from Cal Poly are watching as I throw shade their way. That said, Sam then transferred. He also got a prestigious internship, which was really cool. We don't need to go too much into that, but it suffices to say that Sam is a pretty good coder, and he's good at doing projects. And maybe I'll just let you talk a little bit about what you're doing now, what your experience was, and maybe anything else you want to say. And I'll start there.
Cool. How you guys doing? I'm Sam Mazzari. Everything that Mr. George said is true, except I'm not a very good coder at all. That's the one thing I've learned. I'll even try, if I have some time, I'd like to show you guys some code. But just, right off the bat, I transferred to Channel Islands. This is my second year. I got most of my core and GE stuff done at Hancock, so I pretty much hit the ground running at Channel Islands. I already had a little bit of an interest in computational physics, which I'm not a physics person, never been a physics person. All the physics I've done has been in the classes you guys are in. I mean, it's fun, I like it. It's not really my interest, but like Jorstad said, I'd had the opportunity to go up and participate up at Stanford for a little bit, an internship that really opened my eyes to kind of the applied computer science. I found an application that wasn't something like making apps or just the stuff that other people find more interesting than I do. I'm not really into app development. I mean, I'm into writing stuff that I can use. So I got kind of interested in the simulations and computational science side of things. I got to Channel Islands, and my very first day of my first class, my first professor told us how his area of research is lasers, computational physics, simulations on lasers. And the one thing from my experience at Hancock that I try to take with me everywhere is to speak up. When Jorstad originally, the first time he ever brought up, any type of distributed networking or multi parallel processing, anything like that, I was scared, but I raised my hand, and it started a conversation, and the conversation led to one thing, led to the next thing, and it almost seems like, those conversations, those seeds, those interests, being vocal about what you're into, or just wanting to experience new things. It's like that leads to new experiences and new things. So I've been lucky. I've been blessed to have that. It's been I'm in my third semester from transfer now, and that first professor that told me he was into lasers and he did all that. I took one class with him. I took a second class with him. I told him, hey, by the way, I'm interested in computational physics. Maybe not lasers, but ice was cool. And that led to a couple more conversations over the summer. And now I work for him as an undergrad research assistant. I'm actually funded. He got me funding. So I have it's basically a scholarship. It comes from the National Science Foundation, which always sounds good and looks good. And what we're studying right now is, okay, maybe not what we're studying. I'm helping him make a proton spectrometer. What exactly is that? I don't know. Has a lot to do with protons bouncing around and causing other physical reactions and stuff. It's interesting. I really like simulations. I think the easiest way to explain kind of how they work would be to think back to collisions. how you do collisions in physics class, and then discretize your time. Time increments. All a simulation really is it's a set of initial conditions, and then you discretize the time. So after 1 time unit, what happens? After 2 time units, what happens? So I'm using a toolkit called Jean 4. That's my attempt at saying it with a French accent. And what it does is it gives you as a researcher the tools necessary to build the geometry, the actual physical modeling that you're doing, to select what kind of physics processes are involved, and then to track and select what data, what kind of, basically you just add whatever you want to it. Jean 4 will track it for you. There's a lot of default materials and particles that come with it. It's pretty interesting.
Is that based off Java, Python, something, or
C++? Oh my gosh.
C++, old school, baby. I love it. I love it.
It's not just C++. It's not like Wagner's C++ back when he used to teach C++. This is an extremely well-written, high-level kind of C++. The most basic examples that it provides to learn from, I had to go back to the drawing board and really dig deep for my C++. It's been a few years. I did get the opportunity to reach out and talk to real life researchers. One named Zach that works for Battelle off in Ohio. It's really interesting. He, as an undergrad, did some Jean 4 work. I was able to do some calls with him. Soon I'm going to do a meeting with an Air Force. He works for an Air Force contractor. Anyhow, they do some simulation stuff. I'm trying to set up a meeting with him. Like I said, I'm not the best coder. That's one thing I've recently learned, is that I'm not as good as I thought I was, but I do want to be better. Yeah, it's not about knowing everything. It's just really about trying. Mr. J, if you want to, can I share my screen?
Learning. Yeah, do it, man. Go for it.
Yeah, all right. So I'll just let me find my virtual machine that I'm using right now. That might be it. Let's take a look. That's the wrong one. All right. Got a bunch of screens up right now.
Sure.
There we go. That looks like it's it right there. All right. Can you see my screen?
Yes.
All right. Sweet.
Yep.
So
Are you using PyCharm or something else? Or
close. I'm using Sea Lion right now.
Sea Lion. Sorry, my bad. I forgot you said C already.
Oh no, it's cool. It looks just like PyCharm because it's JetBrains. So if you guys don't know, go to JetBrains' website with your school ID, apply for an account, and you get to use all their professional tools for free. Every year or so, you just got to update your current school stuff. So using Sea Lion, let me close up some stuff here. So my code that I'm writing right now is inside of my test. All these tests under here are example simulations that came with Jean 4. So let's go ahead and let's just run one.
Sure.
Looks like I've already built it. All right, let me go into the terminal then.
While that's getting ready, were you pretty good at the debugger, or did you have to learn that? Or
the debugger is hard. So if you're talking about GDB, the GNU debugger, that's real hard. That you just got to kind of crack down and learn that. But for the Sea Lion debugger, it was a pretty quick learn. Watching your variables, learning how to keep a watch list and step through, kind of knowing what to look for and where really helps. Let me.
Sorry, I didn't mean to interrupt.
Sorry if this takes long. But
it's all right. I was just looking. It looks like we're actually a little bit ahead because, oh man, we had a brutal.
Oh, really?
Brutal lab yesterday.
I remember that.
That's my fault. I made some typos in the code. Yeah. Lab is always bad, no matter what. Somehow it's always bad.
Who caught it? Who caught the?
A number. It was a really strange one where I think there were 4 unique errors on different questions because I read a lot of different versions, and so it was just multiple students caught multiple errors, and it was just a frustrating experience for everybody.
Well, that's part of it.
Yeah, that is part of learning, right? You probably remember catching all my typos in the workbook. Sam caught perhaps as many or more of my physics 161 typos than any other student. Anyways, yeah, all right.
Yeah,
you guys were my proofreaders that time. That was brutal. You know the deal.
Oh man.
Oh, by far, Nick, by far. These guys were finding so many every week. It was crazy. So you got the filtered version. Yeah.
It prepared me though. It prepared me. I learned to actually look and think about it and not just kind of, sometimes it's you look
not
at it
trust your instructors all the time. Yeah.
Yeah.
It's true, right? Everybody makes mistakes, even your colleagues, and knowing when to stick up for yourself, knowing how to know when you're right and when to call them out is a key thing. Yeah, for sure.
And knowing to double check so that when you do approach them on it, they don't just look at you and say, "No, bro, you're wrong. Redo it again."
Yeah, right.
Yeah, which that happened a couple times. That's frustrating, you know.
Sure.
So what we have here is we have a simulation set up. So you've got your universe. You've got one shape, 2 shapes. I believe that first shape is actually made from water in this example.
Okay.
Let's go ahead and let's run it. I haven't ran this one in a little bit, so I'm gonna go to the README real quick and see if well, I forgot to do that. So let's is it in here? Nope. It should have been in there. Wait. Yeah. All right. So V1. If you guys aren't comfortable with the terminal, you'll want to get comfortable with it soon. All right, here we go. So let's go with, let's do this in interactive mode. Yep. All right, so we'll run this first command. Oh, that didn't do what I thought it did. There we go. Okay, so these commands are just setting up control. So verbose 2, it's saying, hey, control, I want the level 2's worth of information. I mean, it's one more than level 1. I really don't know anything other than that as far as that goes. For the tracking is like as it moves through space.
Keep a trail.
Keep a trail, as well as keep a trail for every other particle it comes in contact with.
Okay.
Yep.
Oh, I see.
There you go. And then run beam. So this is the cool part. So run beam, we actually call it the particle gun in code. It's a particle gun, and it's what's going to shoot. It's what's going to shoot our particle. It's going to shoot.
Where do they come out of?
It goes left to right. So I'm sorry. It goes from the negative x coordinate to the positive x.
So it'll start like somewhere right here and go that way.
There it is. Yeah.
Oh, whoops.
It'll go from left to right here.
Oh, so left to right.
Yep.
So it'll start right here, go through the water, interact with some particles, and they'll start streaming out.
Exactly.
Okay.
And then, so this, sometimes it crashes my course because it is highly threaded, but this should be fine. There it is.
Whoa.
And so you got 10 events, all 10 were good. And this is what it looks like.
So it does the momentum scattering during the collisions, probably in the center mass frame in the code, huh?
Well, you know what?
Oh,
I'm
okay, my bad.
With the code than I am the physics. be real honest right now. But yeah, and then so
I got you.
It keeps track. It keeps track, and there's an output file. Yeah, but if I'm not mistaken, what we're looking at are I think that's an electron we shot. I'd have to dig through it.
Sure.
But for this example, it's an electron.
I got you. So what is do you know what kind of your dream goal with this project is? Is there like a goal that you're working towards with all these sims?
Yes, there is.
What's the big picture takeaway for that?
My professor wants to build and sell a new proton spectrometer,
Oh, that's right. You said that. My bad.
something that hasn't been used yet. His background comes directly out of like research labs,
Mm-hmm.
and he sees a need for it. There's a market for it, and he wants to do the research.
Okay,
He,
cool.
yeah, in our research team, I've got two other students, undergrads, with me, but they're working more of a mechatronics thing. They're For them, it's more about physical lab equipment, laser blockers, laser tables. I think it's called a laser table, a light table.
Yeah, optics bench. Yeah,
Optics bench. There it is. They're doing stuff, components for that right now.
interesting.
So yeah, it's pretty cool. He gave me an option between this and a bit. He's about to start a big project uh, on sand, like the effects of dredging sand. Nobody's ever really studied it. And so what he wants to do is come up with a way to simulate sand moving around the coast. It's kind of a big project that hasn't started yet, but it reminds me a lot of FD Map in Antarctica. It's basically sand instead of ice, like the Stanford stuff.
Gotcha. Oh yeah.
So yeah,
Very cool. So just kind of bringing it back to where these guys are at. So what do you think about the preparation at Hancock, and is there anything that you maybe wish that you would have done, or is there anything you're really glad you did do, or you know what I mean, like for the transfer process?
yeah,
And you could be particular to, because you're a CS major proper, right? So you're CS, right?
yeah. Well, yes.
So we've got a lot of CS majors in here, probably 20-30%. Is there anything specific to them maybe that you'd have to say? And maybe I'll stop your screen share real quick just so your face is up. Is that cool? I didn't mean to cut you off there.
That's perfect. That's perfect. So what did I wish that I'd done? I wish that I'd done more um, like personal projects. I wish that after I did the microcontroller GUI stuff with you, that I had actually gone a little further and implemented like the controller part of it, stuff like that. I really kick myself for not doing that, only because the one thing after Hancock is that your assignments and everything you do become large projects. Everything becomes larger, and it's all about managing and and tools. When you're writing two classes, two like uh, uh, classes in Java. When your homework or when your final only is 10 functions, two classes, and some type of GUI, like that's cool and all, but it's real basic. One of my first assignments this semester was writing a CPU scheduler for a multi-core processor. And just the stub code, just the stuff they gave us to write was it was so difficult to navigate through it. It was so difficult to understand what it did. You have to have you don't have to, but analytical skills are important. Being able to not just look at something and say, well, this is what it is. It's, well, what does it do, and what would it do if? I think that's a real important thing, is what would it do?
If?
Yeah. I think that a lot of my hangups, I was focused so much on memorizing and understanding definitions that it was harder for me to step back and look at the bigger picture of things. I wish that that's what I'd done. I wish that I would have stepped back, looked at the bigger picture, and then now I'm reaching out to people in industry. Now I'm blind writing emails to grad students at universities to get a feel of what they're doing and how they feel about their research advisor. Like I'm trying to be more out there. I'm trying to be that's exactly what it is. Being out there more. Yeah.
There's probably, to some extent, it's a natural progression, because you do need to have some basics before you can reach out, because you feel a little, so you maybe could have tried to reach out more, but I would argue you probably did a lot more than the average student at this level too, right? Let's be straight here. So you always wish you could do more, Is there any, yeah, but so you're probably on a great trajectory in terms of when you're reaching out and doing those things. In your junior year, you definitely want to hit that right away. But if you could do it as your sophomore year, that'd be even better. What about, is there something that was particular? Well,
Oh, your video.
here's a question. We
Okay.
did a lot of lab write-ups and oral presentations and torture like that. Has that helped you as a CS major at all or not?
100%. 100%. I thought that CS was going to be about me being in a little room by myself dealing with a computer, and it's not. Okay, yeah, it's code, but you have to work in teams. You have to present your information. In one of my classes, honestly, it doesn't really matter if the code works or not. You know, you have to be able to explain it. You have to be able to understand it. With you in physics, oh my gosh, your presentations could be torturous. Standing up there sweating and just forgetting everything, forgetting what you meant to say. But that's what school's like. I transferred to CI and it's all presentations. My theoretical probabilities class, all theory, high level theory, we were presenting every 2 weeks. Yeah, every 2 weeks. And then well, what do you have to present on in that? Like, well, we have to take all that theory, write some code about it, and then make graphs. I'll never forget that. I remember emailing you, I think, right after the first one. I went in and I had to write some stuff in Python, and he wanted something like 4 or 5 really gnarly graphs, and I dug deep into my Excel graphs and I did them, and my team got an excellent grade. But when we were done, I remember thinking, okay, here comes the hard stuff, and I was like, any questions? And the professor didn't have a single question. I was like, what happened here? Yeah. I remember, Mr. J, I remember you being able to look at a single graph for like 5 seconds, and then at the end of the presentation, you'd be like, wait, can you go back 4 slides? And you'd go back 4 slides, and they'd say that their rate of change was like 1.5, but the graph looks like this. You'd be like, I'm sorry, but that doesn't look like 1.5. And then
right.
And it's like, wow, you know, I think that it was great practice and it prepared us. Instead of being overly nervous once I got to Channel Islands, I was actually more prepared and more comfortable, and I was able to understand the material better. And you get better grades, to be honest with you.
You get faster at making presentations too, so they're less onerous. I mean, figures always take a long time, getting the right thing that looks nice. How important is formatting? Is it a big deal or not? Because I spend some time on it trying to whip people into shape, especially because I know they have to take DOM. But in your classes, is formatting a big deal or not really?
Well, the answer is yes, but they don't. If I didn't already know that formatting was important, then I would have had poorly formatted presentations and I would have gotten poor grades, but I wouldn't have received that feedback. They don't. It seems like they don't go, okay, well, you got 20. I deducted you, 10 points or 15 points just because it was messy. Okay, but that doesn't leave with much, One thing I remember is the size of my font. That was a big thing. What was it? 22? Minimum was 22?
At least 18.
18, that's what it was, yeah. And then for anything bold, that was 22. I try to keep my images large. That was one thing I also learned from you. And then when you're going to compare about the differences between images, you might want to have them sequential. Knowing that that's another thing. I just did a 15-slide presentation. And I didn't have to actually present it. But I just created 15 slides for a presentation in about an hour and 40 minutes because I was mistaken on the due date. I got an A-. It was because I understood the formatting and I understood how to put it together.
Yeah, I got you.
Yeah.
Do you care if we get a couple of these questions from the chat?
Let's do it.
I see somebody says, why'd you choose Channel Islands? I was considering the school, cost of living, etc. Do you see the chat there from Nick and also Nate Dogg?
I do see that. Nick and Nate Dogg. Yeah, let me take this. Holy shit, even me? Probably even you. That sounds very familiar. Why did you choose Channel Islands? Okay. So I didn't choose Channel Islands right away. I actually got into some really good UCs, but my living situation, my family situation, everything, I postponed transferring for a year. And then this was a mistake I made. I discourage you guys from making a similar mistake. When it came time to apply again, I was hell bent on going to Cal Poly. I figured that my grades were great, almost a 4.0. I satisfied I felt like almost everything that they would have wanted, and I only applied to Cal Poly.
Ha!
And then I didn't get in, and it really hurt. It really hurt me as far as like confidence and stuff like that, because just the year before I was getting in full rides to Berkeley, Merced, a couple other schools, and then all of a sudden I'm not into Cal Poly, and I didn't apply to anything else. Luckily, the Cal State Apply, I think it's called, they reached out and they were like, we noticed you didn't get into any schools. We'll give you the option of these 3 schools, and Channel Islands was one of them. And I'm originally from Ventura County.
Sweet.
So it just kind of went together. In this brave new world we got going on, where everything seems to be virtual, why not go to Channel Islands? I mean, it's cheap. It's the cheapest state university there is. They try to use OpenStax textbooks everywhere that they can. They really go out. I mean, they really go out of their way for students. It's a lot like Hancock, just on a little bit larger and more bureaucratic scale.
It sounds like you're getting good technical knowledge. I mean, you're doing some serious stuff down there too.
It's a state school, so they want to have graduates that know how to work, that know how to do the industry standard is kind of like a thing. So as far as like IDEs go, the operating systems class, they want everything in that terminal. They want everything with Vim and GDB, the GNU debugger. Everything's hardcore. You got to know how to write. You got to know how to make CMake and write CMake lists. If you guys don't know how to do that, those are pretty fundamental, basic development kind of things.
Yeah. See what Nate Dogg had. So having all of your GE done.
Just hitting the ground running. Okay.
Was that good?
Was it good? No, I don't think so. I still have what's called upper division general ed. So all the GE that I got done at Hancock, that would be low division GE. There's 3 upper divisions. I've taken one of them actually. They're pretty cool. I never actually got my languages requirement out of the way, so I still have that. It's difficult, man. I don't recommend it. And you already do. You're gonna have already all your GE done. I recommend taking something in there that's not as intense. Like I'm taking 3 programming heavy classes this semester, like real heavy, but I'm also taking a sociology class. So it kind of helps. But if I didn't elect to take that sociology class this semester, I'd be taking a 4th programming heavy class. That's hard to do.
So just making sure I understand. I remember liking having a GE course to take during my junior or senior year, because you know how it is as a tech major. All your tech classes are so hard and so time consuming. Your GE course is like easy A, lightens your load, gives you time to complete all your crap, right?
Exactly. And you want that. You want that. On one hand, it's cool to have your GEs done because you figure you get right into the meat and potatoes and get it done quick. But it can mess with your head a little bit. Things get tiring. And just like George said, just like you said, it's kind of nice to be able to take a class where you don't have to think too much.
And I know this is kind of unrelated, but for me, it's nice to have a class to meet people that are not super nerds.
Yeah, that's different. That's very. So
I like nerds, don't get me wrong, but it's nice it increases your ability to meet other people and hang out with non-super nerds.
Mr. J, they actually know how to use a smartphone. That's what blows me away.
Whoa, that's crazy. I don't know how that's too much. Let me just get back to coding. Yeah. Let me see. So I suppose we should probably get close to wrapping it up, because it's been about a half hour and I should probably get to work with these punks.
Yeah.
Any final takeaways about the transfer process, or anything that you want to leave them with, maybe?
You know, don't feel out of place once you do transfer. That's easy. It's easy to feel out of place, but you get over it pretty quick. Don't be intimidated. When it comes to applying for universities, apply for all of them that you can. If you can reasonably apply, because sometimes there's fees, sometimes there's not. If you can reasonably apply to them all. Or if they reject you, go through the appeal process for all of them. You don't have to choose your university right away. You can wait to the very last moment. That's probably the one mistake I made in my academic uh, career so far that I regret the most. Uh, yeah, yeah.
All right. So everybody, let's give Sam some of those cheesy whatever thumbs up or whatever from Zoom. I'll give him the clap or something.
Clap. Don't give me the clap, Mr. J.
Oh, sorry, my bad. Well, I'll give you. How about I'll give you the birthday cornucopia of fun. All right, dude. So, and then Sam, I really appreciate you coming by and taking the time. And let's, yeah, if you guys have questions, you could email me and I'll forward them on to Sam. If you have any questions about his work or life or Channel Islands or something, I'm sure he'd send me an email back. So, all right, man. I'll catch you later. We're gonna do RC Transients and KVL.
Oh man, sorry I can't stay, guys, but I've got.
All right, so I hope you appreciate that. I like trying to bring in the guest speakers just because that stuff matters more than my class. So hopefully that's good stuff. All right, let's pick up here. All right. I got a giant picture of Ryan on my screen. All right, that'll make you holler for sure. All right, so let's see, where were we here? Oh, this nightmare still. Oh gosh. All right, so let's see. Let's start with the screen share and get this rocking out. Oh, that's 110. Wouldn't it be nice to just be doing 110? So let's pick up, let's see. I think we did some resistor problems last time. We did some, and I think we started doing KVL. So what I want to do is maybe do a KVL problem before the break and then get into RC transients after the break. So let's just start here and see if you remember anything. Let's start with this one right here. So 27.13, I'm going to draw it up. And then remember, why don't you try to use the KVL rules? This is on page 125. So page 125, you've also got the rules there at the top. And so see if you can just remind yourself of the rules that we briefly discussed. Write down the equations, and then let's see what we can do for 27.13. You can do 27.12 on your own later if you want. Okay. I'm just going to write it up myself, and then I'll share my whiteboard. And I'm going to check my solution really quick, just so I do the same color code for these currents. I'm going to try and match my solutions real quick. So just a second here. Oops. Is this okay? So it looks like I used purple for current, red for, okay. So I used purple for the currents. And I think I called this one, loop 1 was red. And I think I used green here, loop 2. And so I think I got everything labeled there. I'm ready to go. Okay. So let's kick some butt on this here. So we've got this circuit. You can see that there are 3 currents. Remind me, someone, by unmuting or throwing it in the chat, how many junction equations do you think we need to write down? How many loop equations and how many junction equations total? What do you think?
2 loops and 1 junction.
2 loops, 1 junction.
Excellent. Because we have 3 currents, we know there's 2 obvious interior loops. Excellent. And so the remainder is 1. That's what we're going to get from the junction. So maybe I'll label this up here as junction 1. And I could have used this spot down here. So the junction is wherever you have a T or a multiple branch. So I'm going to write down my equations. You can try and beat me to the punch. And obviously, if you want, you could follow along with the solutions, but maybe try to do it without at first, just to see what happens. So you could pick anywhere you want to start. I'm going to start right here. I'm going to call this ground. Or that's where I'm going to start all my loops here. Okay. So you don't have to draw that. That's just for fun. Some people draw ground like this. That's fine too. Oops, that's a little sloppy, but you get the idea. All right. Some kind of a triangle or something. So that's just where I'm going to start. Okay. And again, you can choose where you say ground is. You could choose where 0 volts. Not if you're wiring a house, then it's already been chosen for you. But for a battery circuit that's not connected to ground or not connected to your household sockets, that you can choose ground. So in this case, loop 1, let's see, I'm going with this. I'm exiting on the plus terminal. I would say plus E, because I'm leaving the plus terminal. I'm going, loop direction is with current. So I would say I1R.
Would that be plus 2E?
Oh, you're right. Thank you. Sorry, my bad. That battery is 2E. Thank you. And then this is minus because current and loop same way. And then minus like that. Don't forget the equals 0. A common thing to do at this point is you could divide everything by R. So if you wanted to, you could actually, notice if I divided everything by R, it just looks a little bit neater. And now everything has units of what?
Current.
Exactly. Amps, current, something like that. So we see that if you divide everything by R every time, you'll get units of amps every time. And then why is that useful? This equation, the junctions are always in units of amps. And so what you're doing is you're basically making sure that every equation always has the same units before you start messing with the algebra. Is that required? No. You could do whatever you want. Okay. So for now, I'm going to leave it up here just because I want to focus on making sure you understand where these terms come from. But a common trick is to immediately divide by R, so all 3 equations would have the same units of amps. Next, loop 2. All right, so I started here. Notice this loop, I tend to choose to go with the batteries if possible. That just makes sense to me. You don't have to, but this particular one, it was drawn that way, so we don't get a choice. So I'm going to get a plus E because I'm exiting the positive terminal of the battery. I'm going with the loop direction, so I3 goes with the loop. I get a minus 2 I3R because this is I3 and that's a 2R. So there's the 2R and there's the I3. And then loop is going with, and so there we go. Finally, my junction, ins equal outs. 1 and 3 equal 2. And then almost always, just like I usually divide these immediately by R, this one I almost always, for me, it makes sense to think ins equals outs, because that's easier for my brain to remember. And then I immediately rewrite it so that all the currents are in order. Could you have just immediately done this? Sure. And then you just say everything coming in gets a plus sign, everything going out gets a minus. Whatever works for you. All right. So there's the equations. Now at this point, I'll pause and see if there's any questions. Any questions on that? Nice. Nice. Now I am going to divide through that R just so it's sitting in here. So next step would be divide everything by R in the first equation, just to make it look nice. I'm going to do the same thing with the second equation. It gets rid of that R and that R. What do you think? How would you approach this? We have 3 equations and 3 unknowns. It turns out students do need a little of work at this because we're so used to usually only doing 2 equations, but sometimes we get 3 or 4. What do you think? What would you do? What would you try? Anybody? Let's say we were trying to solve for these 3 currents. Sorry, I interrupted.
I would do the matrix setup.
Okay, that's true. And that would work. Do you agree we're very close to the matrix setup? You could do that. Let's say you didn't want to do the matrix setup and you wanted to just solve for stuff. I guess if you didn't want to do the matrix, one thing you have to do is basically get rid of one of these letters at a time, right? So E and R are known. We're looking for the unknown currents in this case. You could add these 2 equations together or subtract them, actually. If you subtract them, you get rid of I2. Of course, that introduces a new problem because then down here, I2 is still there. So that's maybe what you could do is do the following. Since this one is already solved for I2, maybe you should just take this and plug that in right there and right there. What have we done? We have got, if you do that, I2 no longer appears in the equations. So that's nice. So you have to be clever about how you do this. Now, this is what I would recommend. If you did this, put a star next to this equation or something on your paper and be like, I have already used this equation in both of the other ones. Don't just put it in one, put it in both of them. Then you're done with that equation. Next, you say, okay, solve this one for I1 or solve this one for I1 and plug it in, or you could solve this one for I3 and that one. So it's just algebra. I don't want to spend all day on that, but I do want you guys to make sure you do a couple of these just to make sure you feel okay on doing the algebra. The matrix method works pretty well. However, for a 3x3, you should be faster doing just the math by hand if you practice these at all. And so this is actually a lot of times just a simple problem like this will appear on a test because it's got 2 loops. You have to get 3 equations right, do some algebra, and that's enough. If you can handle this one, I know you can handle a 3 loop or a 4 loop. So in general, if you can handle 2 or 3 loop problems in the homework, you should be able to handle the test questions on the final or whatever. All right. So let's go take a look and see if there was something in the solutions worth noting when we actually do the algebra. I can't spend all day on the algebra or we'll never get anywhere. All right. So in this case, here's the raw equation. Here's the modified. Notice I moved those voltages and just got rid of all the minus signs. So here's some different equations like that. Look at this cool one. I thought this was funny. I3 equals 0. So this is super fun, right? So let's go back and look at it. So when you solve those equations and did the algebra, what I'm telling you is that this current is 0, even though there's a battery right there. Isn't that crazy? Let's try to understand this by doing the node voltage. Now, I've been dancing around alluding to this several times. Now I'm going to make you guys try to understand this thing. So let's say you did all this information and we found out, I'm going to bring that back up on the screen just so I have it here for a second. Let's say we find out the following information after doing the algebra. E over R, I2 equals E over R, and I3 equals 0. I just found this problem by chance, and I left it in because I thought it was so fun. All right. So here's the idea. If you wanted to, you could put in a number here, right? If you want to try and get a feeling for this, let E equal 1 volt. Let R equal 1 ohm. That means E over R equals 1 amp. So that's what I'm going to do so that this next part makes sense. Now, ground, and I'm going to check what letter I used. I think, sorry, what color I used. Give me just a second. I used pink. Pink and blue. Okay. So let me see if I've got a pink here. I had a pink. All right. So I have no idea how well the colors are going to show up over the internet. Sorry if they don't. So the idea is we're going to set this value right here as 0 volts. That's supposed to be pink and that's supposed to be red. Sorry if you can barely tell the difference. Okay. So this is supposed to be pink. Now, as I go from here to here, what is the voltage right at this point? Well, I've gone up 2E. E is 1 volts. That means at this point, this is 2. And just to stress this, the change in voltage as I go across the battery, delta V is 2E. So notice this is 0. I change by 2E, so I end up with 2 volts here. Now, as I go upwards, I'm at this spot right here. Well, there's no resistors between here and here. Ignoring resistivity of the wire and assuming that's negligible, this should still be at 2 volts. So far, so good? Now, let's think. The change in voltage as I go across a resistor, delta V here is going to be I1 R1. So that's I1 R, which in this case, I1 is 1 amp. And I see that 1 amp times 1 ohm should be 1 volt. So when I do this, this should be a change of 1 volt. So what is the node voltage right here at this junction? At this junction, the change is 1 volt. Should it be 3 volts or 1 volt?
1 volt.
1 volt. The current is going with the loop direction, so we expect it to drop. So this should be 1.0 volts. So notice I don't need to keep going. I already know there's 1 volt here. Let's keep going the other way now. As I go this way, there's nothing in between. So this is still at 0 volts. As I go up, I went across this battery. The change in voltage is E, which is 1 volt. Notice, what is the change in voltage for this resistor?
0.
So that's why there's no current. And so this is a really funny thing. This battery is sitting here doing nothing. It's going to last forever because it's not doing anything. Isn't that trippy? Very weird. So it turns out this battery would not end up used. Now, in practice, what should happen is if these were real batteries, this one would start to wear out. Its internal resistance would go up a little bit and the current produced would go down. And then all of a sudden this battery would start getting used. And so it might start doing something weird at that point. But at least for a little while, we would expect this battery to not be consumed at all. The energy inside of there would not be consumed at all. And so I just wanted to point out this particular thing. There is a difference between node voltage, the voltage at a specific spot in the circuit, versus a change in voltage, delta V. Delta V means potential difference. So there's a change in voltage of 1 volt here, whereas this node voltage happens to be 1 volt. All right, that's enough on that. But are there questions on that while we've got it up?
Yeah, I did the algebra and it worked, but where did the R come back in, the E over R?
Sorry, it cut out a little.
Where did the R come back in for the E over R?
For this one?
Yeah, since we divided it out earlier, where did it come back in?
A voltage is E over R times R. Or are you wondering where this came from in the original equations?
Yeah, I thought we divided R out earlier.
Oh, but remember, it stays in the, okay, let me share screen and I think this will make sense. When you divide it out, it's still on the E term. You see it now?
Oh, okay, I see, yeah.
It ends up staying in because of that term right there. And then the R's drop out. Oh, you got it now?
Yeah, just missing that right there. Thank you.
Yep. All right, cool. Good, good. All righty. Cool. And so just kind of, I tried to draw this up for you. There it is a different way. And so, yeah, and this is what I was saying. If you change either battery voltage because one of them starts to wear out, perhaps, then blah, blah, blah. Oh, look at this. This is really crazy too. We could have used any resistor up there instead of 2R and it would still do the same because the voltages are the same. All right, so there's that. All right. So let's try one more of these, take a break and get to RC transients. Let me find one in the workbook really quick that we could work on here. This one, I'm going to let you work on at home because I did a really thorough job here. This one, you probably recognize this from lab last night. All right. And so this is an interesting problem. I'll leave this for you to do at home. It's a 2-loop circuit, but notice the following. I did something interesting here. Notice what I had you figure out here. Determine numerical values for each current and potential difference, E prime. So what I did, notice, look at this. I gave you one of the currents. If I give you one of the currents, something else in the circuit could be unknown. And in this particular problem, basically, I gave you the current through one of these batteries. I forget which one. So that's probably, yeah, so I'll let you read through this one. Oh, no. Charging battery. Oh, so that's this one. So I think I gave you this here is I or something like that. But notice I didn't give you I2 or I3. And so the idea is, how do you charge your battery? How much voltage do you need to get this battery to charge? Or maybe you could learn something about how long would it take to charge a battery if you use certain power supply, et cetera. So this relates to a charging type problem. And so what you could do is you could learn this problem, and basically it's a slight variation where instead of giving you all the currents or asking you to find all the currents, I give you one of the currents and make you find the other 2 currents and the the charging battery. All right, so I'll leave that for you, and that's kind of a fun one. I want to focus more on, let's see. Oh, this is a pretty good problem. Yeah, that's a fun one. That was an old test question once, and that surprised me that some people had some trouble with that. There is something sneaky in this one. We haven't done a lot of calculations with power, but I just want to point out this one has percentages and power in it So there's some good stuff about power to learn and how many light bulbs can you blow before you blow a fuse. So this is kind of a good practical question here. So, all right, let's try this one. Let's try this one right here. And let's just worry about getting the setup. And notice you could try to get the matrix if you're into that, or at least write down the equations. So let's practice that again. All right. So I don't know. Yeah, let's do one of these. And I don't know. At some point, this should become formulaic, and I just don't want to stop too soon, because what if the question comes up right now? So yeah, this is good, because how many loops do we have? We have 3 loops. And this is 27.18. There's clearly 3 loops. How many junctions are we going to need?
I would think all 3 of them.
We're going to need 3 junctions. So, yep, because we have 6 currents. All right. And so I'm going to go ahead and write I'll write the loop equations. The junctions are pretty easy. So let's at least do the loops. Okay. And then maybe what I'll do is I'll stop my screen share for a second. And I'm just going to do it. So you've got the problem right in front of you, hopefully. I'm going to do it as well. And then we could see here, it says everything has resistance capital R except for the weird one down there in the bottom right. Okay, so that's easy. So loop 1, if you pick some starting spot, let's see what we get. I'm going to get plus I5R plus V1. I3 doesn't really matter right now because there's no resistor in that, right? So if you have current through a battery, it's not going to show up in the equation. If you have current through a resistor, it shows up in the equation. And then I think we get minus I1R equals 0. And, all right. And we could double check that in a minute, but for right now, I'll double check it. The loop goes against the current, so it's plus. This is a battery I'm exiting on the plus terminal, and the loop goes with current I1, so it's a minus. Loop 2, I'll just start right here. I get a minus I4R because the loop direction goes with that. I exit on the positive terminal of V2, and then I'm going against I2R, so that's a plus. I'm going against I2R, and then, I exit on the negative terminal, so I get a minus V1. Let's go to loop 3. Loop 3, I'll just pick some random spot to start. I'm going to start the left side. So I get a plus I6 capital R plus I6 little r, because there's 2 resistors there, and you kind of obviously combine them, plus V3. I exit on the plus terminal, and now I'm going to do, let's see, plus, because the loop is going against I6, so those are both plus. Exit the plus terminal. This next one, I'm going against it, so I get a plus I4R. And then last one is minus I5 back to home. And it's totally possible that in some problems, every single term is going to be a plus. That's not a big deal. That just means you missed one of the directions. You'll figure it out at the end of the problem. You don't have to know all the directions before you do the math. All right. And so okay, so I'll leave that at this. Are there any questions about those? You may have the terms in a different order. You may have, that's it. So, but yeah, if you have the terms in a different order, that's not a problem.
So it doesn't like really matter where we start from.
No,
Because like you said, it's like if you're going in that direction,
you'll get everything
that's
eventually.
just a different order. Like, but it's still the same thing. Okay.
Yeah, right. Because I could have started right here at V2. I hope that was minus I4R.
Yeah, minus I4R.
Yeah, so right, I could have started right here, and then you get there, or I could have started right here. It should. So
So
it
it's
doesn't
kind of
matter.
hard to really mess it up if you just obey, obviously, kind of the
Yeah, yeah.
rules.
And yet, every year,
You can
about
mess
half
it
the
up.
class screws it up, and
Yeah.
the reason is it's very hard to not make a mistake, as we've all seen in this many minus signs. So I don't know if you noticed what I was doing. I was double and triple checking. Here's another tip. After you get them all done, go through and check them one last time before you do the algebra, because you don't have a lot of time on a test. Now, again, I don't know if you remember, I told you kind of what I was expecting to do for the test. At least one of the questions is identify. At least one of these is write out, or I think pick at least one loop equation and show you can get it right. So that's the way I can give you some partial credit. And then there's probably going to be one where you have to do something with it and do some calculation. But right now, the most important skill you need to work on is identifying these numbers. How many loops, how many currents, how many junctions. Number two is correctly writing the loops. Correctly writing the junctions is useful, but that's pretty easy. And so because, I don't know if you remember, I sent an email, one of the many frickin' emails from yesterday or this morning or something. I said, because yesterday's lab was so brutal, I'm not only giving you 4 free points, I'm telling you straight up right now, I'm not going to give you a oral exam question on the final about KVL. So I'm not going to make you, at least from the homework, right? I might put a KVL problem on the final exam and then it's fair game. But I'm not going to say, oh, did you do question 27.19? You better show it to me. I'm not going to do that to you. Now, I might put something on about the RC transients in the last half of this. But so that's a good thing, because if you feel like you're good at algebra, you could just go through all of these problems, make sure you get the right list of equations and unknowns, make sure you find something that works. And some of them are going to be a little bit trickier to check. So there's going to be one or two you might have to go all the way through. For example, if you did this one down here, notice I didn't label anything, right? So because I didn't label them, your equations might look different than mine, but you need to know how to check that. You need to know that if all of your signs are negative and the terms are switched, it's the same thing. Because remember, if you flip every term sign and multiply 0 by -1, you get the same answer. I'm going to pause there. Who was that? Was that
That was
that
me. That was
Travis?
Travis. Yeah.
Did I address your question?
Yeah, that was good. Can I ask a really quick kind of like,
Yeah, anything.
I mean, I feel like this is going to be like a dumb question, but on number 2715 on that circuit number 2, from like
Let me
looking
bring
at
it up
that,
so everybody's looking at it. Hold on.
yeah.
27.15, circuit number 2.
Yeah, so like when we're looking at that, so the current, so like if we had the loop 1 at the top, so if we had the loop 1 like yeah, right in there. So like let's say that's our loop. Is like how do we know, like how, because wouldn't current, or couldn't current flow both, like
Yes.
I don't know, I'm trying to think about like the way
Okay.
it would flow, like wouldn't it go through both, or go in on both sides, like
Okay, so let's take a look. So this is a good one. Let's do this one. At least part of it, and just sketch it out. So we have, and I just need my whiteboard to do it justice, okay? So let's say we have this crazy looking circuit. I'm just trying to stretch it out so I have some space to draw inside, okay? All right. And then in this case, there was another resistor right here, right? So this is problem number, what was it? 27.15,
Yeah.
circuit 2.
Yep.
Sorry, I just squeezed that in there. I should have written that somewhere else. All right. So now, and then let me make sure this was number 1, 2, 3. Nope, it wasn't. It was 1, 2,
And then
3.
3, and then 4's up at the top, and then 5. Yeah.
Now, here's a trick for this type of problem, right? What I would do is I would label the battery current as I0. Okay, so notice I0 coming in, this has got to be I0 coming out. And the reason I do that is it turns out I really only have 5 unknown currents that I need to worry about, and then I can get this last one with a junction rule. So I do have 6 currents. Travis, since you spoke up, how many loops, how many junctions, how many currents? What do you think?
I mean, it looks like crap.
Sorry, I
I'm
didn't mean to
thinking-
put you on the spot. It's
No,
okay to
good.
take your time.
I need to know this. Yeah.
Yeah.
I mean, there's the 2 loops obviously to the right, but then
Okay. And I think you said this one and you were okay with it going that way.
yeah.
So we'll call that loop 1. And then how about we call this one loop 2? Did you pick a particular direction or do you care?
No, I mean that doesn't.
So is that fine with you?
Yeah. Mhm.
And again, this might be different than the solution I wrote up. It doesn't matter,
And then
right? That could be fixed later. I'm just gonna make this a little prettier. Sorry. Okay. What were you thinking
Then-
next?
wouldn't there be another? No, I mean, is there another loop you like? Because there's the out, like, because yeah, there's that one. Yeah. Okay.
Loop 3.
Yeah.
How many total currents do you see?
I mean, there'd be 5 going through.
One
mean-
for each resistor in this case.
Yeah, and then the one from the battery.
So how many total?
So 6.
6 currents.
And that means
How many
there'll be
junctions would you use?
3 junctions.
Hopefully and then let's pause. Is everybody cool with that part? I'm going to label them. Oh, actually, I'm going to make Travis do the work here. Sorry. I1, do you agree I1's probably going this way and I4 is going this way?
Yeah.
And then do you agree I5 is probably coming down here
Yeah. And then
and I2? And
be
your
going down as
question
well.
that you wanted to talk about, I believe, was about I3, right?
yeah, that was kind of, yeah.
Okay. Which way do we have to draw the arrow?
I mean, well, from loop 2,
Short version, doesn't matter at all.
okay.
And so pick one. Nice job, Nick. So you call it. What do you think? So the idea is take a guess and it's okay if you're wrong. How about we just say this way? And now what's going to happen when you do a bunch of math, bunch of blah, 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 blah. At the very end of the problem, let's say you get a positive number for I3. Oh, I guessed right. If you get a negative number for I3, oh, I guessed wrong. I guess it flowed the other way. And that's
Okay,
it.
cool. Dang. Okay.
Is that what you needed?
Tight. Yeah, that's perfect. Because
Yeah.
I don't know, that just seemed weird. Because I was like,
To know without
gonna
doing all
flow,
these resistors.
you know.
Yeah.
yeah, like it's not gonna flow
Yeah.
both ways.
Yeah.
Thank you. Awesome.
Yeah. If you guys are interested, here's how electrical engineers might do this. So in another, if I redrew this circuit here, electrical engineers do something weird. So let me just draw this really quick. And so I don't want to spend a lot of time on this. There are some videos out there. I don't know how many of you've ever heard of mesh currents or mesh methods. We're not going to do them because it's not mesh currents. They're not They don't have physical meaning like the KVL does. So, you know, as a physics teacher, I like problems with physical meaning. Let me move this board in just a second here. Okay. So what an engineering class might do is say, there's current flowing this way, and I'll call this I1. They'd say there's current flowing through this loop, I2, and there's current flowing through this loop, I3. And now just because these are different, I'm going to label them with primes. So what they do is they actually say, well, there's these currents. And then if I want the current right here, the current right here would be a superposition of I3 this way and I1 this way. So the current right here would be I1 prime plus I3 prime. The current right here would be I2, etc. And then the current in the middle one, which kind of alludes to what Travis was mentioning, which is why I'm bringing this up. This one would be I1 this way minus I2 that way. And so you could think of it as current flowing both ways if you're an electrical engineer and you do a thing called mesh currents, but that's different. We're not doing that. Their sign conventions are different and engineers are crazy. So I can't help it. I'll let you learn that in an engineering class. All right. So make sure you tell Dom I said that. All right. Those engineers, they're crazy. Physics people are completely normal. All right. Where were we? I don't know what we're.
I was just asking that question. That's how we got down that path.
I think it's a good time for a break. Travis, did that? Oh yeah, that's right. Yeah. So
Yeah, that was
that's
perfect.
yeah, that was the idea.
Thank you
there.
very much.
All
Awesome.
right. And I think I could keep doing these, but at this point, me doing them for you is not going to get you there. It's got to be you. So let's take a quick break, and then we'll come back in about 8 minutes or so, and then I'll start teaching you RC transients. Okay. And we might end up being about a half a lecture ahead, which I'm sure will get chewed up somewhere later. So we should keep the pressure on today. All right. Take your quick break, and I'll see you back in a few minutes here.
I have a
go
quick
for
question. I think it'll be quick. I hope it'll be quick.
Yeah.
Looking back at problem 2718, there's the node right below V1.
Hold on, let me get it on screen here.
Yeah.
It's easier to communicate that way in case anybody else cares. The node right where?
Right below V1. Is that, I'm just kind of having a hard time conceptualizing that because we say current flowing in equals current flowing out, and there's none flowing in.
Mm-hmm.
So
what does that tell you? So hold on. This is a great question. Ryan asked this. Ins equals outs, right?
Mm-hmm.
Okay. So what is the total amount flowing in?
0.
What is the total amount flowing out?
Oh.
So clearly this tells you what? One of them must have been drawn the wrong way.
Oh.
So now you know, okay, I expect at least one of those currents should be negative because it's impossible for them all to be flowing out. So all that means is one of them has to have a negative sign, which means one of them must have been drawn the wrong way. Excellent question. Got it?
Yeah.
Take a guess.
Yeah, thank you.
Look at this other node. Okay, so let me draw some nodes here. So let's say there's an orange node, there's a green node, and a blue node, right? So those are all the possible junctions. So in this case, we had 6 currents. We turn out we don't need all the junctions. Let me catch up on the chat there. Hold on. Oh, I see. Okay. All right. So this is a good question, right? So clearly other people were wondering too. Which junction indicates or so? Oh, cool. What do you think? Which of these junctions might also be nutty? Using Nick's terms. What's the other nutty looking one?
The blue one.
Okay, so let's do the blue one. Trey, what are the ins?
All 3, I1, I5, and I6.
And the outs are 0, right? So just based off that, I can't prove it, but I suspect 5 might be wrong because that would fix two equations. That doesn't mean 5 is the wrong one, but and you know it could be multiple of the other ones. It could be. It just depends, right? Look over here. Let's say, what about these two batteries, right? What if one of these batteries is a lot stronger than the other one? What if 2 is really strong? Well, maybe current flows this way, and then I4 might be correct. But what if V1 is really strong? Then maybe it's so strong it goes, I have no idea. So rather than think about it, this is the thing. Why think about it? Write something down, get the problem done, move on. And that's the trick. At the end, think about it. This is a lot like, suppose you have an elastic collision between two balls. And let's say there's mass 1 and mass 2. And you know this one's moving this way at V1 initial. All right. And this one's just, let's say this one's moving this way at V2 initial. Okay. And after the collision, I don't know which way these things are going to go. So I just draw them both moving to the right, call this V1 final. I draw this one moving to the right, call it V2 final. And if I get a minus sign, that just means they're moving to the left, right? Same idea. You draw your currents. Who cares which way? At the end, if you get a minus sign, I guess it was going to the left or up or down or whatever. And remember, current is just the size of it, right? Current technically is not a vector. Current density is a vector. So it's okay to do that. Is that helping on that?
Yeah, I think that was super helpful.
All right. Okay, so now we'll take a break. So we'll give you 8 minutes from there. So 5:57. All right. All right, let's check that out here. All right. Do you guys like having the guest speakers come in? I know I do that a lot. What do you think? Yeah.
Yeah, that's good.
Hopefully I cut them off about right. I mean, you got to learn stuff here, but you know, I figure that's good information that you really can't get. All right. If it ever gets too much, you just let me know, or all right. You could always send me a private message if I'm letting it run on too long and just be like, I'm stressed out about class. Could we get to lecture? But 20 minutes is usually pretty good. It's time well spent. 30 today, but let me get rid of this crap. Hold on. Okay, get that out of there. It distracted me. And then, all right. So, all right. Now I think we're finally ready to do something pretty fun. It starts to get pretty dynamic now. I'm even smiling because it's slightly interesting. Either that or it was that Diet Mountain Dew I had for breakfast. One of those two things is making me happy. I won't tell you which. Or maybe it's a little bit of both. Okay. So an extra half gallon of caffeine can't hurt. So I'm going to start with the circuit, and I just want to, yeah, Taco Bell breakfast, baby. Here we go. No 10-piece McNugget meal here. We're going straight to the bean burrito. All right, so I'm going to start with the really simple circuit and finally get some spice. Okay. That's right. Okay, so we haven't done this yet, and maybe I'll start, and this is a classic circuit. So you've already done this circuit in a sense. In all of your original capacitor circuits where there's no resistor here, what happens to a capacitor over time? If I close the switch, what's going to happen to this capacitor?
It's gonna charge up.
Charge up. And once it gets charged up, how much current flows, do you think?
Whatever.
None. So now what we're doing, and that happened before when you just had bare wires, but the resistance was just really small. So the charging happened very rapidly because there was no resistance. So let's say we put in a resistor. When I close the switch, it's reasonable to think it's going to charge up. It's going to take a little bit of time to charge up, depending on the capacitor and the resistor and the battery, et cetera. And so we're going to try and learn about how long it takes to charge up, what the voltage and current look like as functions of time. So rather than just having a current that's either on or off, this is going to be a current that changes. It's a transient current. Okay, it's there for a short period of time. So this is called an RC transient circuit. So when you close the switch, there's a small current for a transient amount of time. So let's label this as R and C. Now, I'm going to show you some tricks in a minute, but I'm going to try doing this in a little bit different order than I usually do it. Let's say I close this switch. Okay. And let me tell you this too. Before you start taking notes, I have already written up everything here in the solutions in the question. Let me just show you where it is if you want to follow along here. Let me share screen. So we are now up to RC transients. So let me just show you where we're at so you know what we're doing. So we're going to look at this circuit, RC transient circuit. It's on page 129. And before I go on, I just want to read here. I'm basically working out 27.20A right now. So I'm going to try and give you a feeling for this. Then we're going to go back and we can do this all again, or you can read the work that I'm about to do in the workbook later. So my thought was a lot of students have a lot of trouble with this. You may want to just watch and not take notes for a little bit. And then afterwards, you got it all written up. And so you could go through it again after class. All right. So that said, let's say we have a battery right here, and I'm going to actually force myself to deal with the polarity right now. All right. And hopefully I don't make a mistake in the polarity. If I do, I'm going to flip it later. So at some point, I hope you agree that this plate would be positive and this plate would be negative. Think, right now, if I put a positive terminal here, aren't electrons going to move that way? The electrons are going to move towards the positive terminal of the battery. Inside, we have some magical chemistry fairies that are going to push the electrons through. And then over here, the electrons are going to move this way. And we expect to see the electrons end up on this plate. They're going to be removed from this plate and drawn upwards by the battery. And then remember, negative charges going this way is the same thing as current flowing this way. So current is flowing this way. And as a last note, remember, inside the capacitor, no charges jump the gap unless the voltage is crazy big. And that's not happening. But inside, there is an electric field, which is analogous to a current that we will learn about in the last month of class or last week of class called displacement current. So yes, there is even an electric field that's analogous to a current in there. So we're going to, it's too small. Let's not draw it. So yes, there's even current inside of there if you consider electric fields. All right. Is everybody okay with what the red arrows mean versus the blue arrows? Blues are electrons. Red is the conventional current, as it's called. So now, in this case, I guess I'll label this as I. And maybe I'll label this thing right here as the electron, E minus. That way you know what that is. I'm going to do KVL. And let's pick a random spot to start. How about right here? Let's call this ground and write down KVL as we go around. All right, so when I do this, I get E. Now I'm going with the current. So I guess to be clear, I'm assuming this is my loop direction. We only have one loop, but we could still do KVL. KVL is conservation of energy. So as I go around, I'm going I is with the loop. I get a minus IR. Right? And so now we have to be careful here. The voltage on a capacitor, right? There's going to be some voltage here. And then this is the one that I sometimes screw up the sign on, but I'm going to assume for right now, if I'm exiting on the minus terminal of this capacitor, I should subtract the potential difference across the capacitor. And I think this will all work out. So far, so good. Now, I could rewrite this. Does anybody know another way to rewrite voltage on a capacitor? What's another way we could write that in terms of C?
Charge divided by capacitance.
I think so. Q equals delta V C. So if I take this C and divide it, I could rewrite this. So I'm going to do that. Q over C. I guess you also have the live stream if you want to go back and watch this again too. So you could take notes with the live stream if you really need it. Now let's look. Why would I do that? Two of these variables are directly related. Which two variables in here are directly related? This is a bad question, but maybe it'll work. What do you think? Yeah, it's a bad question.
Is it current and charge?
Yeah, that's what I was trying to think about. Both of these have charge in them, don't they?
Yeah.
So I should be careful when I say directly related. I didn't say directly proportional to, so I'm in the clear. But notice this. I could actually rewrite this equation in terms of current if I do what? How do I change this into current? What would I have to do to each side of the equation? Or what is that relationship? Remind me. What's the relationship between charge and current?
Is current charge over time? Okay.
Something like that. And we're going to do dq dt. Very good. Amps per second. So that's a bad glare. There we go. Charge per second. So coulombs per second, and it turns out it's a derivative. So do you agree if I take the derivative of this equation, I could get a relationship for current and time? Think about it. If I take a derivative, I'll get current and its derivative. I got time in there. What is the derivative of the battery voltage versus time? What do you think? How much does the battery voltage of a typical battery change every second? Is it a lot or a little bit?
Pretty small.
Pretty small. Like think about your phone battery. It doesn't go from full to empty in 1 second. It takes a couple hours, hopefully, unless it's my phone, which is terrible. So, but yeah, so I'm going to assume if I take a derivative of these, let me get that minus sign back in there. I'm going to take a derivative of each term here. This term is basically constant. It's going to drop out. So what am I left with? I get negative R di dt minus, what's ddt? I get a 1 over C. What's dq dt?
Current.
I make. There we go. Whoa, there's a chair there. All right. All right. So notice I'm running out of space. I need to write this stuff up there. I want to keep this. I want to keep this picture. So I'm just going to erase this line and just start working with this. Actually, I got one more line here. I'll just lower this down a little bit. So notice I'm going to move one of these to the other side. So, and you know what I'm going to do? I'm going to solve this for di dt right now. I don't know. So let's say di dt, work that out, solve for it. What do we get? Di dt is going to be, this goes over to the other side. So I get an I and a 1 over C, but I have to divide by a negative R. So I think what you get, double check if you get negative 1 over RC times I. Just take a second and work that out really quick. This comes over and becomes positive. Divide by negative R. I think I got it right. And so that means I did get the sign right up there earlier. Huh. What do you think about that? Does that look familiar? Man, sometimes this equation can be a real drag. This is low velocity viscous force from Physics 161. Chapter 2, workbook. Acceleration is non-uniform. I know we did it in 161 and you probably don't remember. It was on page something or other. But yeah, this is an equation we've worked on before. This is low velocity drag. And remember, this is not impossible to believe. This is like a pump. A resistor is like drag. And a capacitor is like a spring a little bit. So anyways, yeah, it relates to those things. So, okay. I need to do some work on this. So let's pause and see if there's any questions about any of this procedure I went to get through here. This is your chance to ask now before I have to erase the picture. Remember, I got the notes too, but yeah. Any questions on that? Let's hit it. So when I do all this, I'm going to get an equation that looks like this. What was it? It said di dt equals negative 1 over RC times I. Whoa. Let's get it on the board there. All right. There are some things you should notice right away. What are the units of RC? Let's do the units. What are the units on this side? Somebody.
Amps per second.
Nope. Oh, wait, amps per second. You're right. You're right. I was right. I was thinking coulombs per second. I forgot I solved for I. You're right. Okay, so this has got to equal. The negative sign has no units. This is amps. What has to be the units of this crap?
1/seconds.
Seconds?
1/seconds.
1/second.
So, I need a letter that looks like T, but isn't. Any guesses? How about a Greek T? Tau, lowercase, is going to be, this is supposed to be a tau. So if you're not sure, tau, there's my lowercase tau. That's going to be in units of seconds. All right. That's what we need to make. So govern how long it takes to charge a capacitor. RC. The bigger R and C are, that's going to be a unit of time. That's going to be the characteristic charging time. You could tell just by looking at the units. More on that in a second, and I will prove that to you. But in this case, tau is called the time constant. Okay, so the bigger your resistor, the longer it takes to fill up your capacitor with charge. That seems plausible. The bigger your capacitor, the longer it takes to fill it up with charge. The bigger the battery makes no difference. Smoke that in your crack pipe tonight. Okay, so in this case, it turns out the value of the battery doesn't affect how long it takes to charge. It's just the resistance in the capacitor. Trippy. All right. All right. So now just know that tau is RC. Okay. All right. How do we solve this? Give me a solution technique. What technique should I apply to figure this out?
What
Looking for,
specifically
like,
do you want us to solve for?
Sorry, thank you. That would be good to tell you what to solve for. I want to figure out I as a function of time.
Oh, cool.
I want to get I. There's an I on both sides.
Integrate with regard, or no? Well, I guess you wouldn't have any.
Yeah, I'll give you that. That's fine. If you integrate, it's kind of tricky, but what do you have to do before you integrate?
separation of variables.
Separate before you integrate. So this is the first differential equation technique anybody learns. We did it in physics something, and I said, you're going to use this, so you don't have to do these problems, but you'd better. So now we're going to see if you did it. That means get the I's with the I's and the T's with the T's. So here, in this case, if I want to integrate, I need to integrate an I integral and a T integral separately. That's how I solve this. Well, let's think. If I want to get the I's with the I's, I'm going to move that over here. And then I'll bring this over here. And there's no other T's. So at this point, this is now a doable integral. I separated the variables. If I do an integral here, now you could do your integrals however you want. I'm going to do them how I want. And if you don't like it, too bad. All right. So in this case, I like to put in the values. A lot of other people like to do the plus C's. This is a physics class. We're going to base this integral in reality. Give me a reasonable starting time. What's a clever number to start at?
0.
0.
That sounds like a reasonable starting. So that means I would start at I at time 0, right? So I'm just going to label this I initial over here. And then up top, let's go to some final time. What would be a good name for the final time?
Oh,
Pick one.
T.
T would be nice, but strictly speaking, mathematically, that would be a circular reference between the integrand and up top. Tau is not good. Tau is a constant that depends on this. So I would say t final. Then after we do the integral, change it to t like Trey suggested. So strictly speaking, mathematically, we can't go from the integral of dt to t. That would be a circular reference. I like 6.657 if tau is less than 1. Turns out 5 time constants is, yeah, anyways. All right, let's do it this way. All right, so what's this integral?
Natural log of I.
Yep, and we're just going to call it log in this class. And notice when I stick in the limits, it's that. So natural log when you stick in the limits is going to be this. And then this is a nice way to do physics problems by having the limits. Notice the units drop out, so you can use amps or milliamps, and the logarithm can still be computed. Again, when I say log, I mean natural log. That's just the way physicists talk. Over here, what do I get?
Negative t over RC, or t final.
Yep, yeah, and then I'll say, how about I do this one and actually stick in the limits? Evaluated from 0 to t final, which is equal to negative t final over RC, which is I think what he said. And then at this point, after you've plugged in the limits, why not change this to t over RC like Trey suggested? So I'm trying to be strictly mathematically rigorous here where, yes, we've got our limits, and notice the following. In a calculus class, they always say, don't forget your plus C, don't forget your plus C. By sticking in the limits, we don't have to forget that. It's already built right into the system. We're saying I'm going to go from some initial current to some final current and some 0 time to some t final. And so I don't need a plus C anymore.
Would it still be a negative? Would there still be a negative
So,
sign?
oh, and there should be a minus sign. Yes,
Okay.
it's absolutely negative. Yep, right there. Yes.
Yeah, just on the end.
Yeah,
Thank you.
yep. So now, what was the goal? What are we trying to do?
Solve for current with regards to time. Right?
Which one of these variables is that?
That's the class.
Which one of these is current as a function of time? Which one of these currents in the limits corresponded to t?
The final.
The final. So what am I trying to solve for? I final. What do I do?
Exponentiate both sides.
Exponentiate both
That's the term.
sides. Or e to the both sides if you don't want to think that. So here we go. E to the both sides are exponentiating. I get I final over I initial. Remember, all this is written up for you. Is that's a t over tau. Remember, tau was that. Cross multiplying, I get I as a function of time. I'll just write I final.
You're going a wee bit off the board, just so you know.
Yeah. Give me a sec here. So what I get there, sorry that's so sloppy. I'm just running out of room here. Let me just start here. I just need a little bit more room. That is the current as a function of time. So you could just call this I of t, right? Now we know, okay, it's an exponential decay for the current. How can I get the charge on the capacitor as a function of time? Any thoughts? How did current relate to charge? Remind me.
Is it a derivative?
A derivative. So you could actually integrate this equation. And so we see, and then wait, what if I need the voltage across the resistor? Well, I've got this. What if I need the power delivered to the resistor? I've got the current. Power is I squared R. I just square this. What if I need the energy stored in the capacitor? Well, I know Q because I could do. So once we get this one piece, all the rest is doing a bunch of complicated integrals, and we could do this. Gosh, I just wish there was a shortcut to make this less painful. Don't you? There's got to be a better way. Let's take a look at it. All right. So that's the background. You're never going to do that again, but I think it helps to see it and understand it. I just wanted to show you that you get these e to the craps, okay? And where the tau comes from. That's all we needed that for. From now on, that is not the way to do these problems. This is the way a professional engineer would do these, all right? So let me make this just a little bit smaller with my zoom in the way. Okay, let me get up here. This is what you really do. All right. This is the right way to do these problems. We have an RC transient. I want you to draw 3 pictures and understand them. Notice there's going to be t equals 0 minus. This is the time just before the switch is closed. So the switch is open for a long time, and just before you close it, that's 0 minus. 0 plus is going to be the instant after the switch is closed. So just after the switch is closed, right? And then notice this fact here. In this particular problem, the capacitor is initially uncharged. The capacitor, the standard way of saying this, preserves its voltage from the t equals 0 minus picture. So if the voltage here across the capacitor was equal to 0, just after you close the switch, the voltage is still 0. The charge hasn't had enough time to build up on that puppy, right? Okay, charges can't move instantly. They don't move at the speed of light, right? It takes time for the charge to build up on the capacitor. So when you close the switch, its voltage will not change because it takes time for the charge to move. Now do KVL. Think about this. If you do KVL, this voltage is E. The capacitor's voltage is 0. How much is left for the resistor?
E.
E. So what's the current through the resistor?
E over R.
E over R. You know its voltage. So I'm going to drop the delta every once in a while, just in the interest of time. And I don't care if you do it. I tried to be very thorough, and we've talked about node voltage. So you in theory can do this now. So now let's think. Let's go to this final picture. After a long time, we call that the T infinity picture. The capacitor is fully charged. How much current is going to flow when this thing charges up? None. Think about it. If charge was still flowing, it wouldn't be charged up yet. It'd still be charging. So once it reaches full charge, I know the following. I know I is equal to 0. Well, if I is equal to 0, what's the voltage across the resistor?
0.
0. So what's left for the capacitor? What voltage? E. And what's the charge going to be? It's EC. So EC. I told you I'd keep saying it. All right. By the way, over here, what's the charge on the capacitor right now if there's no voltage? Hopefully you agree there's 0 charge, there's 0 voltage. So notice the following. If you know this would be the, give me just a second. I'm going to call these the initials. This is just after the switch has closed. These are the initial values of the charge voltage and the resistor voltage and the current. So the 0 plus picture is considered the initials for this equation up here. That's the shortcut equation. This is the infinity picture. These are called the finals. And it turns out if you can write down the initial state and the final state, you could take that and plug that into these equations. And it's so much faster than doing pages and think how long it took us to do what we just did compared to the integrals. This took us about a minute, maybe 3. But that's a lot faster than doing all those integrals and possibly flipping a sign and worrying about minus signs and integrals flipped upside down or having to. This is the equation that we can use for RC transients. Whoops. Oh, so let me get this nice pink border. So this equation here, all you have to do is say, let's say you want to get voltage as a function of time across the resistor. The voltage across the resistor as a function of time is, well, what's X final? So in this case, if X is resistor voltage, I come over here and I say, oh, well, it's 0 plus, what's the initial resistor voltage? E over R. And then it's E to the negative, oh, wait, sorry.
It's E, isn't it?
Yeah, minus, oh, you're absolutely right. I misspoke. Thank you. Thank you. So we get E, and then we minus the initial again, minus the final, which is 0. And then I write E to the negative T over tau. All right. All right. What if I wanted to get the voltage across the capacitor as a function of time?
That's got a quick question.
Sure.
Okay, so you're plugging in the voltage where X is.
That's right.
Does X, like, can we replace that with anything else that we're trying to solve? Is that what
You could,
like
exactly.
X?
And that's what I was just going to say. So X could be the voltage, charge, current, or the resistor voltage. Let me speak. It could be capacitor voltage or charge. It could be resistor voltage or current, but it cannot be energy or power. Is that okay?
Yeah, thank you.
Yeah, so X can be any one of these symbols that I've labeled in the initial or final picture. And so by knowing this trick, you don't have to do as much math, and you get it right, and you get some physical understanding when you're drawing the pictures. So this is just a better way than doing a bunch of math without understanding physics. All right, so let's see this. And Nick, I heard you speak up, so I'll put you on the spot here. So let's say we wanted to use this for the capacitor voltage. What would it look like? So what would I put in for the capacitor final voltage according to these pictures?
It would be final voltage. It would be E.
E, and then I would keep going. The next thing in the equation is the initial. What's the initial?
0.
0, and then minus E, and then E to the, and so what he just found, that was it. Nice job. If I factor out an E, notice I get E times this quantity 1 minus E to the negative T over tau. All right.
Is tau, you say tau is R times C.
That's right.
We don't plug tau into that. We're solving, right?
If
We
you,
don't
yeah. So good question. Let's go down here and look. So now what would happen is times can be given in terms of taus, or I'm going to go to a different problem. Let me see if I have one here. Let me go to one with some numbers in it. Sorry. Let's try this one. So in this case, here, if I knew a value for R and I knew a value for the C, oh, shoot. Okay, this is a little bit different. Let me see. Do I give you one where I give all the numbers? Surely I give you one of these somewhere. Oh my gosh, I did it all with variables, the whole thing. All right, but I think somewhere in the solutions, I must have told you some numbers to plug in. Let me just do one of these on an Excel, and we're going to pick up here next time.
Right
So,
there, you have Al as 2/3 RC.
oh yeah, I'll go into that. So we're going to do another day of lecture on this. So trust me, we're going to start with this next week, and then we'll finish up next week with magnetic fields. But let me just show you this really quick. I know I hate to waste your time. If you have to go, I understand. But let me just say we start with let's start with the resistor. I'm going to do ohms. I'm going to be lazy with the formatting. Okay, so let's say it's 100 ohms. All right, and let's say our capacitor is let's do that in farads, and let's say that's 1e negative 3. Okay, so 1 millifarad. Okay, so what would tau be? Tau would be in what units? What are the units of tau? Remind me.
Seconds.
Seconds. Okay, so this would be in seconds. And sorry, I'm using scientific notation here, but this is going to equal this times that. Oops. Oh, I forgot to hit the star. B28 times that. So there's RC, right? And then let's just put in some sig figs here. Wait a minute. Oh, sorry. I typed 8 instead. Oh, I forgot to hit the shift key. My bad. All right. So there's our tau. Agreed? 0.1 seconds. So let's take a look at what this looks like. If I did time in seconds and I set up an increment size, let's say 0.02, and then I'll just, let me get some sig figs because I can't help it. All right, now I'll highlight these and fill down. We'll go for a couple of seconds here. We'll just go that long. All right, so now over here, I could get the voltage on the resistor in volts. Oh, and so I guess we better put in the battery voltage. Let's do it this, V battery. So let's just say it's a 1 volt battery, okay? All right, and sig figs, blah, blah, blah. Okay, and I better put the units just because I can't help it. All right. Stretch this out just a little bit. There we go. All right, so in this case, what would the voltage across the resistor be? Right, we just found that that was equal to the battery voltage hitting F4, so that's a constant, times EXP is the way you write exponents here. That's E raised to some power of negative A6, that's the time, divided by tau. And I'll hit F4 on that just so I have it. This is what that resistor voltage would look like. Okay, and notice it gets really small after a while. What would the voltage on the capacitor look like? I hope this is helping you. I have no idea. But according to the equation Nick just said, it was equal to the battery voltage, F4 to make it a constant, times the quantity 1 minus EXP negative A6 over tau, hitting F4, so it's a constant. Enter. And now I'm going to fill this one down. And now, just because these sig figs drive me crazy, let's highlight these. By the way, take a guess what you're doing in lab next week. You're going to be doing this.
Yay.
This stuff. All right. So hopefully this video will help you understand lab next week. Let's just plot this really quick. And this is what I really wanted to show you. And I know some of you had to go. So Control Alt Shift equals, whoops, Control Alt Shift H. So here, zoom, so many windows. Insert, scatter plot. Let's just do the curved lines. And so in this case, maybe I should stick in a legend because there's more than one curve. Oh, do I have the, series 1 and series 2. So notice this one, the blue line is the resistor voltage. We see an exponential decay. The words you would use are for the orange curve, that's the voltage across the capacitor. It's an asymptotic approach, right? So these are the two curves. We're going to learn more about this next time. If you want to read ahead, you're in a good place to start reading the book now. And you could try and go through that question after class or this weekend or something. And I could show you more on this if you want in office hours. but I do need to get you out of here. So we're going to pick up here next time. Please, next week, even though you don't have a lecture quiz, try and get ahead. Maybe not, if you don't want to get ahead in this class, get ahead in your other classes, but keep working. This is your chance to get ahead because you know there's going to be some horrible experiences later. It's ERT mode. There's a horrible experience every other week. So, all right, I'll pause there and we'll answer questions now.
I have two about the graph you just made.
Okay, yeah, so let me bring that back up.
So would they, both of those, would they always add up to the battery voltage at any given time?
So let's see. How could we check that quickly?
Sum up the second and third columns.
And your prediction should be correct. I'll just do a little ways. You see what I'm saying?
Yeah, that's cool. Okay.
And so that makes sense from a conservation of energy standpoint. Agreed?
Yeah.
Nice. And yeah, okay, good. Excellent question.
I was also
How about I
curious,
bounce? Can I bounce one back at you?
Yeah.
Oh, go ahead. Sorry, go for it.
Is there anything like significant about that crossing point where those two lines?
What value does it happen at?
Exactly half the voltage.
Exactly. Right? Does that make sense? They can only cross because they still have to add up to 1 volt in this case, right? So if you want them to add up, they can only cross right there at 0.5 volts each. What time does that correspond to?
It's like 0.07 seconds.
0.07. Let's see. So somewhere right around there. It's not exact. So 0.07. So notice 0.07 is pretty close to tau. It's the half-life, so to speak.
Oh, okay.
And so the half-life has a logarithm of 2 times tau, which we'll see in one of the answers. So it's very close to tau. Yeah. Is that good?
Yeah, that's cool.
Yeah. And so can I ask you a question now just for fun?
Yeah, sure.
How do you think you could get the charge on the capacitor from here? If I wanted to plot charge on the capacitor using Excel right now, what would you do?
So charge is equal to EC, right?
And then I hit the dollar signs, right?
Yeah.
And now the copyright symbol is just, the autocorrect. So just ignore that. I don't know how to, maybe if I put a space in there, I won't do that. And now I could take the space out afterwards. All right. So then what if I wanted to get current?
Current at the capacitor?
Oh, current through the loop. Now remember, just give me a sec. What if I want to get current? Oh, I didn't draw it. Remember, this circuit was supposed to be this. We had a battery and then a resistor and a capacitor. Let's say I want to get current. Well, there's only one loop, right?
Yeah.
So how would I get current? I'll go back to there. How would you get it?
It would still be delta V over R, right? But
exactly. So tell me what I would type. Equals.
Would it be the delta V? Would that be the sum of, or from the
if I want the voltage, if I want the current through a resistor, I need the voltage across that resistor.
Okay, so equals, yeah, that
B6 divided by
the resistor value, the
A2
star F4.
Dollar signs, done. And so now I have the current. Now, I don't know if you could tell, what would be a logical choice of units here? Probably would make sense to do millicoulombs, which means I'd need to take this number and multiply by 1,000, right?
Yeah.
And so when I do that, And so, okay, that's cool. And this one probably makes sense to do milliamps. So what would I need to do to this one?
Times 1,000 as well.
Divide, right? Or, oh, whoops, no, times. You're right. You're right. I'm sorry. I was going the wrong way. And so there we go. Notice in this circuit, what is the initial current?
10 milliamps.
What should it be? Equals E divided by R, and then we're going to times it by 1,000, right?
Yep.
Makes sense. So sometimes doing the Excel actually adds some understanding for me, because you're having to work with the equations algebra, and so I hope that helps you understand these a little bit better. Oh, do you care if I just keep pushing you a little bit?
Go for it.
How would I get the energy?
Hmm.
And let's say I want millijoules. The energy, let me be clear, by energy, I mean the energy stored by the capacitor.
Is that the 1/2 something equation we used in 26?
Yep. Charge times voltage. Or you could use Q squared over 2C or whatever. But in this case, because I have volts and millicoulombs, I should end up with millijoules. And so I'll just put a couple of sig figs on that. I got the energy there, right? How would I get the power delivered to the resistor?
Is that the V squared over R? Or
Sure.
Yeah.
And which voltage should I use? If I'm looking at a resistor, what voltage should you use?
The column B?
Exactly. V squared over R. What's another way to do it? I'm only mentioning this because for me, I find that I get a lot more intuitive feel for I squared
Oh, okay, I see.
times R. And it's not that what you said was wrong. I just know from experience later on, this helps us understand power and transmission lines. Whoa, I screwed up there because this is I squared. This would be milliwatts, wouldn't it?
Yeah.
Oh, shoot. Oh, crap. You know what? I'm going to do it this way. Here's another way we could do it. We could just do I times V, and then the units will be right, and I don't have to think. So it starts out at 10 milliwatts. Because I was already in milliamps, I accidentally did the conversion twice. So something to note about this experience is usually it's better to not do any prefixes till the very end and then convert all the prefixes over. But yeah, so you have to be a little careful with your prefixes is what we see here.
You just squared some millis and got...
Yeah, exactly. If I squared the millis, I accidentally multiplied by an extra 1,000. So we got 10,000 microwatts, 10,000 microwatts, because a milli times a milli is a micro, right?
Yeah.
All right. What do you think?
That's cool. Yeah, I like doing the equations more and getting a better feel for them.
Absolutely. And I guess since I'm still live streaming, because somebody asked, I just want to point out this one, this one, this one, and this one all work if you're using that x final or x as a function of time equation equals x final. I'm just going to put it up here for posterities or whatever. Yeah, whatever. Plus, what was it? X initial minus x final?
Yes.
Times e to the negative t over tau. And we already saw these other two down here. You cannot do that. Energy and power don't work like that. Basically, yeah, it's a squared equation. And so you just have to literally do what I just did and square the current equation or square the charge equation to get it. So just be aware this big red equation only works for those red columns, not the blue columns. Is that good?
Yeah, thank you.
All right. Whoops. Oh, I don't want to end the meeting. I want to stop the share. All right. And so, so now I think I could probably cancel the live stream for that.